Hello everyone, thank you for coming. So you already know my names. Fast Neural Network, a no-brainer. It's a pretty catchy title, right? So the agenda, I will cover a little bit about what kind of problems neural network solves and what is neural network a little bit. Then we see actually how does it work and why I think neural network is functional. We see how implement a small neural network using functional approach and how to parallelize neural network. All the material on GitHub. So, and then I provide a link you can download and the slide and the source code. Well, this slide really just means this is my email and my Twitter account just to touch base with me. So a lot of material, but this is the main three objectives I wanted today convey. It is by the way, can you hear me? All right. So the neural network really is to solve complex problem, and is actually turned out to be based on simple math, which was surprising for me. Quite satisfied, and it turned out actually that I'm fanatic about parallelism and concurrency. And when I also saw that neural network is easy to parallelize, it was just jackpot for me. But a little bit about you. How many of you are familiar about neural network? What you're doing here? Well, so the first 10 slides probably are like intro to neural networks. So for pretty much all of you, going to be pretty boring. So I'm going to try to move on then. Anybody are familiar with F#? All right, cool. So the source code that I will show later in the slide is using F#. However, it's pretty much very self-explanatory. So you don't need to know F# to understand the code. And however, I use F# mostly because I can fit the code in one slide, which is nice. So motivation for me, first it was the buzzword, right? Neural network sounds super fancy, but I don't have any math background, and I have probably beginner machine learning. I've been introduced a few times for a few project side and some work related. But recently, where I work is a company based in San Francisco. We do natural language interfaces for sport and analytics, and we start to introduce neural network for natural language generation. So I was able to get more exposed, and it's a very fascinating topic, right? So I started to read blogs, and books about neural network. You found all these interesting Greek letters that beside the lambdas, all that was like, I have no idea what this means, right? So my motivation was really the best way to learn about something is to speak about it, right? So that's why I'm here. But when I introduced also to machine learning, I found out something very fascinating, right? So first of all, if you're familiar with machine learning, I think that all you are, you have a bunch of possible algorithms to use to solve your problem. However, there are so many algorithms, right, that for me, the main challenge is figure out the mapping. Which algorithm to use to solve my problem, right? So there are a bunch of those, like linear regression, k-means, just to name a few of those. And the main problem that you always like this friend expert. So you ask him, hey, what should I use here, right? And probably give you an answer, but the biggest mistake you can do is that you ask somebody else. You're going to give a different answer, right? So again, it starts to be very confusing. And of course, we have supervised and non-supervised kind of umbrella that can divide all these algorithms, But it also turned out that it's not that easy because even if you have supervised and unsupervised, even the same algorithm can be implemented in a supervised or unsupervised manner, like it. So it really starts to be complex. But so to me, the main motivation about neural network is that when I was ready to make my research, I was watching this video about James McCaffrey. I don't know if you know about this guy, but he's working in Microsoft Research. And one is told, he mentioned that neural network can be considered almost like a multi-purpose machine learning algorithm, right? Which means that you can use a neural network to solve a different kind of problem, right? So really consider like Swiss knife, right? So you can design pattern recognition or classification using neural networks. So you can cover pretty much a set of other algorithms just with neural networks. So to me, it was like, well, I can focus to learn well neural networks, so I can solve different kind of domain problems, which is just nice. By the way, a little tip that I found out, Microsoft provide you can search online for this. This is just independent of Microsoft. It's just a table that you can navigate through and help you to figure out which algorithm to use, right? You just answer a bunch of questions and just using decision tree kind of thing. So, and I found this very, very useful. So definitely I recommend it. So briefly, what kind of problem neural networks solve? It's not that bright though, huh? I know people complain about my red color. But so now let us solve a bunch of different problems. From, is a pattern recognition for OCR, of course, natural language processing for what I'm being exposed the majority of my work. And, but probably the most famous one, are, medicine and finance, that recent study where DNA pattern or, try to predict the future of the stock market to become rich. But even when you go online, to the, your favorite e-commerce store, you get some recommendation, right? And so how does this work? Well, the system really tries to figure out the similarity between the people that buy, the same item. So really, it classified based upon your chart, your cart, your items in your cart, and the similarity with people that bought more or less the same items to find out probably what you're going to buy, what you propose to buy next, right? So propose some coupon and so forth. And really, what it does really represent a way to predict. Probably it's not really. It can be predict like base time, but really pattern recognition or classification, right? So if this is the classic example. You have like a spreadsheet here with a bunch of information of, in this case, a student with different kind of information like gender, the grade, the age, and you want to detect the sport. Well, neural network is able to classify all this information, similarity, that can be used in the end to figure out the most likely these guys going to play baseball. Okay, so what is neural network? How many of you remember this? Good, because I don't want to feel that old, right? But so that's right. We got exposed to neural network time ago, right? So we have a Clippo. In Italy was like Clippo. I don't know, but provides some information. But of course, neural network is that you think about software, that it based on the neurons that make prediction and is able to decide what to do, right? So probably this is what you have in your mind. You have, neural network. The TX-800 Terminator? Yeah. So we think about neural network really a system that train and evolve with the time, right? Think about, I'm from Italy, so I play the, soccer example here. But if you want to start to play soccer, you like to grow up and make baby steps. And you train, and you start to kick the ball, and then you get better with the time, but you keep training, understand your dribble, and until you reach your goal, right? You get it? Anyways, so you get better and better, right? So who can tell me what is this? Good, it's a cat. So how are you able to detect they're a cat? Because the shapes, probably, the color, the cute little eye there, which is great. But how you can tell the machine to understand this is a cat? So what is this? Who's that cat? Oh. Well, you say blue, a dark suit and a red tie, and you think it's a person. But now you have more information, right? So now your brain is able to detect, wait a minute, I see this ear there, so yeah, it must be cat. So from now on, whenever you see somebody wearing a dark suit and a red tie, it's a cat, right? So, and this is pretty much how it works. The brain, during the time of your evolution, evolve and understand different patterns, because when you were a kid, you didn't know that was a cat, right? Maybe scratch you, then and you figure out with the time, and the brain, evolve, mature, and all this information are assimilated, and you understand that it was a cat because we're wearing a red tie, right? So the human brain, it really can be described as this biological neural network, right? It's this interconnected system of neurons that transmit, signal. And you really elaborate the pattern to figure out there was a cat or you want to kick the ball through electric signals, right? So in this case, I don't know if I pronounce it right. I think it's dendrites. It receives the signal, and based on those input, elaborate and fire out a signal to the axon to reach the next neuron. So they are all connected until you reach the final result. And basically, the brain, the biological neuron, receive input from source, combine all this information during the way, and figure out what's the final result. But the great part, what is very powerful, is that it's adaptive, right? So it grows and it self-learn, it gets better with the time, with the training. So here, well, we're going to talk more in details coming soon, but think about really, a neural network is a set of organized neurons, right, that are organized in subset called layers. So in this case, in the slide here, we have 3 layers, actually, it's going to be 2, but 3 layers of 3, 4, and 2 neurons, right? And the idea is that all the neurons coming from the input elaborate some signal and pass to the neurons of the second layer, and so forth, right? And there is a value that the arrow, we like arrow, right? The arrow that connect neurons to the next neurons are called weight. So the connection weight, and then we're going to see what does it mean with that. But step back, as I mentioned, really, we're going to see really based on simple math, right? Some metric operation, and some linear algebra and equation that are pretty simple. So if you know how to find out the result of X there, you're good to go. You can, you already know neural networks. One little gotcha, the vocabulary. And the problem is that, neural network is such a big technology that, used in different kind of domain from, business analysts, doctors, academics, and developers, and every of those use a different terminology, right? So, for instance, neuron, we don't call it node, right? And the connection called synapse in biological terminology. But anyways, just a gotcha, print out this, probably keep close to your desk. Sometimes it's easy to understand. So, how does this work? Anyone, any questions so far? I don't want to keep it by the end, but sometimes probably better keep in the context. So, all right. So, this is a fully connected neural network composed by 3, 4, and 2 3 layers nodes, right? So the first layer, the input layer, is normally not counted. That's why I said that's probably more considered like a 2-layer network. And as I mentioned, really, you can see how this network consists of interconnected neurons, right? And usually a group in this in layer. And the impulse, the stimulus that is passed from one layer to the next layer is really said that it feed the next layer. It propagate through the network layers until the last. That is, which you get the output, the values that most likely is represent your result. And this process is called feed forward, right? In this case. So the output really, the result really depends on the weight, as I mentioned, the connection between the neurons, and something called activation function. And we're going to see activation function in the coming slide. But really, what does it mean that during the process, we're going to talk probably in back propagation, that this process of feed forwarding, you go through the end, figure out the error between the wanted result and the real output, figure out the error, and then feedback from the beginning to the neural network to self-training. So a little bit more in details here. The most important concept, as I mentioned, is that it's self-trained, but the first, actually, the second gray column there, right, is something called, well, different names. I call it normalization. It's something very important when you implement your neural network. It's a way that you map the input value in some sort of numerical representation that it needs to be in line, right? So this actually is a very important point when you set and you implement your neural network. So as I mentioned, is about find the best set of value of weight neural network, the most likely compute the output in matching your wanted result, right? So initially the weight, that actually was something that was interesting to me in the beginning, that when you set your weight are just random values, right? And then when you start to train your system, this weight, this value just update and get better until reach the point that you're able to reach the result that you were looking for. In this case, the neural network, inside the white box there, you can see there are like several connections. In this case, the connection count in neural network, which is going to be important, especially later, is counted like you have 3, 6, and 5. So it's going to be 3 times 6 plus 6, 6 plus 6 times 5 plus 5. So in this case, it's going to be 59 connection. And you can imagine, as we see later, how this can explode in a huge number of different connections. The hidden layer, the one in green and cyan, something like, is what actually responsible to the computation to figure out the result of the neural network. Okay, so I think I have 2 more slides about the boring stuff, but I think it's important to cover a bit concept here. So perceptron is a simple concept. It's just the building block of the neural network. Right? It's the node, right? In this case, we have 3 input value, which is 0, 1, 0, 2, and 0, 3, that are passed to the perceptron, and this value represent the input that normalized, like can be any arbitrary input. And the value between the input value and the perceptron is the weight, which is important to calculate the result. In this case, the final output for each node is the sum of the product of the weight and the input value, and then apply the activation function, and that's you're going to get the result for that. Now, as you can see here, beside back propagation, we're going to see later, already you can see how this is just a bunch of matrix operation, right? Especially during the training process. It's just of self-updating and some computation and update the value of the weight, which is represented by matrices. So already you can see how easy could be implemented. Don't worry about the code. Actually, this we're going to see later in a expanded version. Actually, it'll be a bit more provocatory. I use some mutable object there. Whoa. Okay, so yeah, so as I mentioned, the connection and the between input and weight are all pretty much matrices operation. Briefly about activation function. This is just a function that you apply to scale the output of the neural network in a proper range. And there are several. Which one to use? Just try it, right? The most common one is the first one, the sigmoid. However, it seems, and again, this is come from what I read on the internet, so it must be true, that sigmoid has some sort of problem with saturation, with the error in some circumstances. So it seems that the tangent, the hyperbolic tangent function start to get more favor over the sigmoid. So training process, as I mentioned, I mentioned about back propagation. There are several other. The most famous one is the back propagation. It really, how does it work? Is simply you get the input, you process until the output, and calculate the error because you know the final value, right? You calculate the error, and then you refeed back the neural network passing this value and adjust the weight until the error doesn't change anymore, it's stable. Seems that the last one, the swarm optimization, is a bit better, however it's lower. And the most common is the backpropagation because apparently it's easy to implement, the most mentioned in the paper. All right, so little tips here that I learned on my own skin. Some nice guys here I want to share with you. Ensure when you initialize your weight, they're random. But you more or less know the range of the weight that can more or less is close to your output. So that's actually going to help to be faster. But now choose the right number of layer or number of neurons for each layer. This is a tricky because there is not any rule or documentation that can tell you which one is better than the other, right? It's about testing, it's about trying until you figure out the best number. And however, the bigger the layer, the more flexible and adaptable is the system. So, usually you say, okay, I'm going to just use a bunch of neurons a layer, but then you're going to run into issues such as overfitting the neural network. So it's all about compromise. Really keep trying and figure out the right number. And the only thing I want to say about this table, sometimes you run in circumstances when you have like some data can be little or a lot, and it depends really the similarity to the data and what kind of issue you run. Of course, if you have a data set that is very different with just a small amount of data, that's probably you run some issues there. Okay, so any question about this part? Everybody knows about neural networks, so probably I should correct me if I say something wrong. I don't know. Okay.
I'll just say two things. ReLU, I come from the vision community.
Okay.
The activation is ReLU is the one that's only used right now.
Which one?
ReLU, it's piecewise linear.
Mm-hmm.
That's the only activation that's used right now in vision. And the other thing is deeper is always better.
Deeper neural network?
Deeper is always better than wider.
Oh, okay.
Now they're going to, we were up to 170, 190
wow.
levels.
Do you think this is specific for your domain or in general?
No, there's theorems for that.
Okay.
You get much more expressive power when you go deeper, not when you go wider.
Okay.
It's exponential.
Cool. Well, thank you. All right, so neural network can be faster, right? So that's why you want to run in a parallelized neural network. So as I mentioned, the connection in neural network can be explode, right? So here in this slide, I think there are over 300 different connections. So when you run this in some machine, the computation can take a while, right? And what I like to think is that if you run a neural network based upon your brain, I hope that you can compute different things at the same time. I'm not talking about multitasking. I'm not good in multitasking, but for instance, if you drive the car, most likely you can recognize the music playing your radio, or you see the red light, you brake. There are a lot of things can happen at the same time. So the same work in a neural network. The brain can send different kinds of signals simultaneously, and most likely the neural network can be computed in parallel. So that's also a bit provocative, but I want to say here. So nodes, they are connected to each other, right? So, and they communicate each other. Sounds familiar? Of course, right? James Bond can do that. So Agent. Anybody know what is an agent? Did I say what it is? Should I say it? No? Yes? Yeah, okay. So agent is just unit computation, right? Is use a asynchronous message passing semantic, which means you push messages, is no blocking from outside the word, and compute one message at a time. So is used mostly for concurrent application. And the benefit about agent is that it's single thread inside. So you compute one message at a time, and you avoid any sort of race condition deadlock that could part of the pitfall of the concurrency model, traditional concurrency model. Compute one message at a time, and the other messages just buffer, so they're not lost. So the great part is that communicate each other, right? So if you think about neural network, they communicate with the neighbors, and only the output the neurons send to the next layer and communicate each other, right? So this is very much in line, with the actor model. Actually, anybody knows the difference between agent and actor? Just digression, probably is not part. Well, so the agent just in process, right? It can be accessed with a memory address. Instead of actor, it's more like out the process kind of thing. But anyways, and this is the best animation slide I've ever done. Look, ready? Come on. Okay, I'll do it again. So you can see this node, right? And really, if you think about each node as an agent, right? Well, yeah. So you can really map the two models together, right? So one great benefit about the agent that I found out when I implemented is that you can actually add or remove agent almost on demand when it's running. So when I was mentioning about detect the right number of nodes, neurons or layers, well, actually, this actually could be a great model because you can just build some sort of API around to remove and add agent as it goes to figure out actually the element of the result. So in this case, is a F#, no compilable code, just conceptual. So we have an agent there that accepts a function, and you can see the agent really receive a message asynchronously, compute the input with some activation function. Again, this is really conceptual. And then pass the output, send the output. So then you can just create your sort of link function. You can connect the agent, right? So when you push an input to an agent, it compute, and when it's done, send and dispatch to all the agent part of the next layer, right? And you can see here just pretty simple, the hand. You just put a couple for each, and you create your. So this is great, right? This is awesome, right? Okay, provocative. I know, that's probably. It turned out actually that it's pretty bad. It turned out, this performance-wise, because unless you really need to build a system like this for some sort of requirement, I would avoid it because the performance really based on the computation of the connection, not the connection per se. So it wasn't terrible, the performance, but definitely there was some. It wasn't that fast. So, and I put some slides here also because I think that when you read the neural network, really the mapping is seeming natural, right? Node, agent, yeah, but it is the implementation wasn't that happy-handed as I wanted. And you can talk to me later. All right, so a little bit why neural network is functional, right? Well, you know that we are functional programming enthusiasts, right? So you can think of neural network really as a function, a mathematical function that gets some input and gets some output, right? So how are we going to implement it? Let's see how briefly we're going to implement a small neural network, right? Well, first of all, we can create some helper function. In this case, the append value is just to add the bias. I would mention the bias. The bias is just this constant that I really personally don't know why. Probably you can tell me why, but it just accepted in all the paper that you should adjust the bias, which is a constant between 1 or 2 or whatever. So we have this function that append the value to our vector we pass, which is our input. Then we have our function. Okay, we append the constant 1 to 0 for the bias, and then we have the layer function here, which pretty much apply a given activation function. Okay. As argument, we have the weight, which is represented by a matrix, and our input, which is our vector, right? So just simply, we have the product of the matrix and vector here, the input and the weight. We map passing the activation function, and we run our append bias. Sounds pretty easy, right? So next step, we have our sigmoid function, which we have some layer, in this case represented by some matrices. I have 3 layers there, right? Then we have these 2 functions here, which actually turn out, you can just compose neural network with our layer function. We pass the layer function with our activation function and our first matrix, and just use the compose operator here, and you build your neural network. And then, of course, you have your run function, in this case, that you pass the layer and any arbitrary input, and you get your result back. Well, the compose operator, I think that's pretty clear. So actually, it turned out that with a simple, function, it's pretty powerful, because now we can fold over a given list of layer. It's a tuple of layer, tuple of matrix and the function, activation function, and then we just, again with the compose operator, fold over and build something more complex. So at this point, we can pass any arbitrary tuple with activation function, and the matrix represents my layer, and pass my combine them and then run it, right? So this is a so I was surprised actually how easy composable can be, neural networks using functional programming. And of course, you run and use a QD with some input, and you get your result back. Okay, so this is probably the biggest piece of code I'm going to show, and actually I don't want to go much in detail, but really what I want to show here, that really neural network turned out to be a bunch of matrix operation, right? So in this case, I just I'm very pragmatic, so I like functional programming, and I like all the nice feature immutability, but I also I think that purity is good at certain limits. So in this case, I use some mutable type inside, and I did it on purpose just because when you want to when the effects are encapsulated in the function, why not, right? And again, we can talk about that later. But I want to just tease a little bit. Anyway, so all these bunch of for loop or matrix operation, I can be easily parallelized, right? So it really is the nature of the neural network, right, that allows distribution of the work with a very small effort, turn out. However, while distribution of the computation, the parallelized computation, can be accomplished easily, sometimes there are computation architecture that the neural network provides. The choice of the architecture can be a bit more complex, right? So it's easy to implement some sort of neural network can be parallelized, but it's all about found the right pattern for to solve your domain. You're going to see what I mean in the next slide coming. However, just basic as they are, neural network are pretty much massively parallel, right? Because if you think about it, this is look a little bit familiar, this pattern, by the way. It looks like a map-reduce kind of pattern, right? We have sort of input, a map reduced to the next layer, map reduced to the next layer, and so forth. So most likely you can apply the same pattern as well, right? So for instance, here in F-sharp, map reduce, we can create our parallel map function. The P stick here stands for parallel sequence. So it takes a function, a map function, in our input, right? It just apply this function parallel to map the input. And the same we have for the reduce function, right? Again, we have our input with the reduce function, and we run in parallel the reduce here, the reduce function here. And then again, we can compose, map reduce pretty easily in functional programming, right? We have our two functions, and we combine them with the two inputs, which, if you remember here, resemble a little bit the composition aspect that we have in the beginning with neural network. Any question about this part? Okay. All right. So how long, by the way? 5 minutes. 5 minutes left? Okay. So, I got 7, right? Okay. Motivation. All right. F-sharp event calendar. I have the link here. It's a great event that run every year. And what it does, it just, people sell their soul for Christmas to write a blog the specific day. This year is great because we built an EPUB, so all the blog, you can download it. But for the blog, actually, I was working with neural networks, so I decided to write something using neural network, which is the classic TSP problem, but in neural network, which is a bit different, right? So TSP, actually, I found out that it's not just a fun algorithm, but actually it's used, like in medicine, from the found some sort of genome pattern or DNA sequences, so I found very interesting. But anyways, so in the beginning, I wrote the code in parallel, and I have like a pretty good performance as expected. However, well, actually, a friend of mine that is this audience found a bug, and actually, but anyways, thank you to fix it. It was even faster. But anyway, so then I found, I'm a paper junkie, so I found this paper online, right? And the paper pretty much apply, the divide conquer approach to TSP, right? And what they use is they use a neural network of using elastic network pattern, which pretty much instead to use a two-dimensional point, use a ring initial and expand the ring to figure out the best pattern. But it turned out they actually, the study used, I think, a K-NIS, is a network, elastic something. But anyways, what it does is it get all the point and try to, and use underneath a K-means classifier to classify the city, or the points, right, in district. And then run in parallel all these districts here to find the best pattern, and then found the closest point to merge, and merge together some sort of with a blend function. So, of course, right, quick demo. Let's run the demo. All right, so I'm not going to go in detail about the code, but again, I'm going to show the link later. You can download it. So the idea we have this point. Everybody can see it, right? Yeah. So here we have some setting about the city, iteration, neurons, and initial learning rate can be arbitrary. So using the setting, you want to have like some sort of, the number of neurons should be like 4 to 5 times the number of the city. And the iteration should be like about 5 times about the number of the neurons. In this case, I put 25,000. Let's put like 15,000, which is way more. But anyways, so I initialize here, and I start. And this is like the parallel process in the back. It takes 3 seconds, 3,400 milliseconds to run, right? 15,000 iteration, right? But, so now we can divide all the city in cluster and run this cluster in parallel and then merge together. Before run, well, let's run it first. All right, it was 1100, which is like 3 times faster, which is pretty nice, right? And this is just with 2 clusters, right? Then you can, of course, increase the number, and you can go crazy. Let's say 6, probably it's not even good, but anyways, yeah, but 500 milliseconds. So what is cool about this approach, this technique, is that if you start with 0 iteration, right? You start with the traditional approach, you just get a mess of line, right? Because I try to figure out which line touches the city and the best, path. Instead, can you start with a circle, right? And then the next iteration is each iteration actually have two steps. Is expand one side, when they have the point to touch the best city, and expand in the back, try to almost like an oval size, to found the other best city in the other side, in the other direction. The point here is that even if neural network can be massively parallelized, it's always about find the solution for your domains, right? There are, like in this case, I found this paper, and it seems actually the right solution for the approach. So always try to go a step further what we try to implement. I know we're running out of time, so I'm not going to go through the code, but I want to just close up with the link that probably useful. So summary, well, I'm not repeating that. The resources here was the paper, and what is it? Actually, the next one. By the way, I'm writing a book, functionalconcurrency.net. This is I have to do it, right? You get coupon here to get 39 discount here. This is the link. Yeah, that's all. Now we have some, there you go. So this is the link. In my workshop, there is actually, it's cool if you want to implement it yourself. There is two folders. One, the full implementation, and one actually tell you step by step how to implement it yourself. So I recommend if you want to have fun and at the same time learn from F#, try with the workshop first, play it through. If any questions, shoot an email, right? And then see how it goes. All right, that's all.